Okay, here we are just to wrap up what happened in class today. I will repeat slightly for anyone who maybe wasn't there or whatever, or wants it to be said again. We have this thing called the Pumping Lemma. The Pumping Lemma is a theorem about regular languages. It says that every regular language has a certain property. But what people use the pumping lemma for is to prove that certain languages are not regular by showing that the language under discussion does not have this property that all regular languages have. And what properties do all regular languages have? Well, like one way of thinking about a regular language is it's a language that can be recognized by a finite automaton. And a finite automaton has a certain number of states and has no power to sort of memorize what kinds of characters in the string have occurred up to a certain point. And so because the deep sort of way of talking about this is to say that if a language is regular, then very, very, very long strings must exhibit some sort of pattern, some kind of repetitive pattern. Because there are only a finite number of states in the machine that recognizes all the strings of that language. And so very, very, very long strings have to basically be looping in some kind of way in order for them to make it through this machine. Okay, more specifically, this is a repeat of what we did in class. We said let A be a regular language. Let M be some deterministic finite automaton that recognizes that language. And M has to have some number of states, so let's call that number of states P. Now, we consider how this machine processes very, very long strings. And we sort of think of very long as being longer than the number of states. And okay, technically, it can be as long as or longer than the number of states. So we say, all right, take a string of this language and let the length of it be greater than p. Let's call the length of it n, where n is greater than or equal to p. And what happens as this machine processes this string? Well, n plus 1 states are visited, and we can call the first state q1. Then the machine reads one character from this string s, and it goes to state q2. So one character has been processed, 2 states have been visited, then it goes to q3, 3 states have been visited, 2 characters have been processed, etc. Since the string is of length n, we will eventually visit n plus 1 states. But of course, n plus 1 is bigger than p, and thus we say that a state must have been visited more than once. This is what we said in class. And we made this kind of, well, here was the argument. We visited n plus 1 states. There are only p states total in the machine. And since this number n plus 1 is bigger than p, we apply the Pigeonhole Principle. And we say, okay, here's where the technical details get maybe a little bit confusing? Not really. What we said in class was, if we refer to the states by these indices, the indices being the order in which those states were visited, then there must be some state which is visited like in the ith step and also in the jth step, such that qi equals qj for some state of this machine. And the picture, which I think is the really valuable part, looks like this. This machine here processes this very long string s, and there is some sort of initial segment in which some substring, which we're calling x, is processed. And then at some point, because of the Pigeonhole Principle, there's this repeat visit to a certain state. So let qi be the first state that repeats. And the first state that is visited sort of again. So here it is. We get to this state, qi, and as this state gets visited again, then there's some sequence of states which is processed, and eventually we end up back in this same state. But if we're back in this state, we've done it as sort of a big loop, and the machine doesn't know, because finite state machines can't know, like sort of how long we've been processing the string or anything like that. All it knows is we're back kind of where we were earlier. It doesn't even know that. We just are back where we were earlier. And then finally, there is this substring z, and then we end and it gets accepted. Y is the substring of characters processed in between the first visit to the state qi and the second visit to the state qi. And the big idea of the pumping lemma is that therefore every long string can be partitioned into these three sections. There's the initial section that happens before the first repeated state is first visited. There's the substring that gets processed on the loop in between when this state is visited and when it's next visited. And then there's the substring that is processed at the end of the string. And in principle, x could be empty, could be the empty string, and z also could be the empty string. But y can't be empty, because we really do need to go from this state sort of at least back to it again in a separate visit, and so y has to be at least like one character long. All right, that's basically the whole gist, and then the thing we did with 5 minutes left was to state the pumping lemma formally, and I'm going to just call the proof like already done, because we just kind of proved it as we were talking it out. So here's the summary of sort of everything we proved. Give me any regular language, there is this special number, and we refer to it as the pumping length. And this special number is this usually quite a big number, but we have seen it's just the number of states of the machine. And if you give me any string longer than this number, then we can partition this string up into three substrings, x, y, z, where their concatenation is just the string s, and then three things. One, there's this substring y is of some length, of length at least one, that the first two sections of this string together have length less than or equal to p, and then here comes the big sort of picture is that since this part y happens on a loop, then any string which has that same structure must also be a member of the language. In other words, if x, y, y, z, if x, y, z is a member of this language, and it is, then since y is the substring processed in between the visit to those two states, then x, y, y, z must also be a string of this language. And x, y, 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 z must also be a string of this language. And so must x, z be a string of this language. So this is what's called, the reason why it's called the pumping lemma is because this activity that we've just done is called pumping. It's determining the structure of any string any long string that this machine accepts, and recognizing therefore by sort of this is the process that's called pumping, by saying like, okay, well, if you visited y, if y is the substring that the machine composed of all the characters that the machine processed during that loop, then you could just very well loop twice, or loop 3 times, or not loop at all. Okay, and then the one small technical point is that, in fact, both the x and y substring have to be of length less than or equal to p. And the reason for that is, I was saying this just as the bell was ringing, we sort of revisit the argument from the last 10 minutes and like refine it slightly. Because in the first half of the board, we applied the pigeonhole principle to say that since we visit n plus 1 states by the pigeonhole principle, and n plus 1 is bigger than p, by the pigeonhole principle, two states, or a state must be visited twice. But in fact, we can apply the pigeonhole principle a little bit, with a little bit more specificity to, in fact, the first p+1 states. So now if you list all of the states visited as machine M processes string S, this is the first state visited, the second state visited, the third state visited, etc. Eventually I'll visit this some state Qi, well, I should say, keep on going until you get to the state QP+1. Now, the actual string is going to be possibly longer than QP+1 if n is longer than p. But what I want to do now is apply the pigeonhole principle to the first p+1 states that are visited. And the exact logic from before applies directly. That since the machine visits p+1 states, but there are only p states, then two of these states must be visited twice. And so two of the states between state 1 and states p+1 must be visited, or a state rather, I should say. It's very hard to say. A state must be visited twice among the first p+1 states visited. And so let's call them Qi and Qj. And so that loop happens before we visit the p plus first state, is the point. And therefore, that is the justification for the part 2 of the theorem, that in fact this initial substring and the loopy part happens and completes before we have visited p states. But we sort of abstract away from talking about the machines because we want this to sort of apply to just regular languages in general. So it's that this first part of the substring and the second part of the substring together have length less than whatever the pumping length is. Okay, good. That was like a long-winded way of redoing everything we did in class. Let's do the one thing I promised we would do that's new, which is use the pumping lemma. Okay, how does one use the pumping lemma? Well, there is a whole method for it, and I am going to do now I'm going to do one example. It is the easiest possible example. It is the classic example, and after I am done, you will do for homework many more, much more difficult problems. Okay, so let's go. Step 1. Just mention the language that you're talking about. So consider the language, I called it big B in class, which is all the strings a to the n, b to the n, such that n is greater than or equal to 0. All right, this includes many strings, a, b, etc. And this language is infinite. It contains strings that are arbitrarily long. This is sort of the classic example of a language which is not regular. Okay, how can we prove that it is not regular? Well, we will do a giant proof by contradiction. And so what we're going to do is we're going to assume that B is regular. Aha! We have proven the pumping lemma for all regular languages. And so what I would like you to do now is to cite the pumping lemma. And effectively, I want you to just regurgitate the pumping lemma right now at this moment in the proof, because I think it has educational value. And so we say, by the pumping lemma, there exists some letter P, the pumping length, such that, well, what's true about this P? Well, what's true is that for all strings in this language, if the length of that string is greater than or equal to P, then that string can be partitioned into 3 substrings x, y, and z, such that 1, the length of the repeating substring is positive. The entire first substring and second substring together have length less than or equal to p. And 3, that x, y sub I, z is also a member of that language for all I greater than or equal to 0. Okay, and I think these proofs are complicated enough that I'm going to insist on like a fairly rigid like structure to keep it all clear about exactly what's going on. So let me just kind of mention that it's like sort of like step 1, Roman numeral 1, introduce your language. Roman numeral 2, like note explicitly that we are assuming that the language is regular for the purposes of doing a proof by contradiction. And then this entire thing is just applying the pumping lemma. Simply state the pumping lemma. Okay, okay, good. Now comes, I think, the most important part of the, well, this is now the hardest part of the proof, I guess, happens right now. Because right now, what we have done is we said, okay, we have this language. I don't know exactly, well, I'm assuming it's regular. So there must be some machine out there, and that machine must have a certain number of states. Let's call it P. So there must be this pumping length. And now we have to sort of, we're in the middle of a proof by contradiction after all, so we have to show that this can't be. And so what we now need to do is to sort of argue that in fact this language is sort of too complicated for it to exhibit this, this sort of repetitive regularity. And what we must do now is come up with a string which like captures the essential irregularity of this language. Sort of what makes this language irregular, this is sort of a very informal way of thinking about it, but what makes this language irregular is that you never know how many A's are going to happen before the B's start coming. And if you were sort of forced maybe to try to recognize the strings of this language with a regular grammar, you would do that thing we did in class where we said, okay, if it's an A, then the next one has to be either a B or another A, and then 2 B's or another A, and then 3 B's or another A, and then 4 B's, etc. And so if you are given many, many, many states, like say 1,000,000 states or something to work with, then you could probably correctly tell whether short strings were members of this language or not. But if you give me a string, if I was only allowed 1,000,000 states, and you gave me a string which had 1,000,000 A's followed by 1,000,000 B's, then my machine simply wouldn't be big enough for that string to be correctly processed. And that's the general idea. Somehow from experience, intuition, understanding, etc., you have to invent out of thin air, this is what makes this a hard math problem, a string that is going to produce your contradiction. And so here, I don't know how obvious this is to you guys, but here, based on the conversation, the sort of thing I just tried to outline, the key string is A to the P, B to the P. This string is going to do the job. Because if my machine has P states, then it can't possibly recognize this string. Okay, but we don't really talk about machines explicitly, we're just kind of like going to use the pumping lemma. So that's step 4. Well, then I would like you to explicitly note that this is indeed a string of the language. So R is a member of B by definition. That's just a fact. And, crucially, it is subject to the pumping lemma because its length is longer than P. So also, the length of R is indeed greater than or equal to P. In fact, the length of R is 2P. Okay, so I'm calling this Roman numeral like 5 and this 6. All right. So, since it is a string of this language, which is longer than the pumping length, then we can conclude that it must have this pattern. So, by the pumping lemma, this particular string R must be decomposable into these sections x, y, z. Okay, and now I'm calling this step 7. Such a math teacher. All right, good. Now, make sure I'm still in frame. Oh yeah. Now, we carry out the argument by analyzing what this string must look like. Well, since, and here I think it's pretty clear, right, that as we talked about on the other board, the initial part and the repeater part have to happen in the first p states. And so, now we say, since xy is less than or equal to p, and the first p characters of our string under discussion, a to the p, b to the p, are all a's, then I know that x and y consist entirely of a's. Then x and y consist entirely of a's. And in particular, what matters to me is that y is composed of entirely a's. So let's say that y has m a's. M greater than or equal to 0. Okay, so what I've now accomplished is an analysis. I'm going to call this step 8, of the structure of the y's. And now, what that means is that this string R, what it looks like, is it has some a's in it. I don't know how many, so I'll just write like A, da, 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 da. Not quite sure how many. That's the x part. But I know that the y part consists of specifically m of these a's. This is the y part. And then the z part, I don't know, and I don't really care right now. That's what I've proven in this step 8. Okay, well, now we pump. What we say is, by the pumping lemma, this is now we use sort of step 3. By the pumping lemma, if x, y, z is a member of the language, then x, y squared z must also be a member of this language. But that can't be, because, well, what is x squared y z, or sorry, xy squared z? Xy squared z is, well, it's going to be x, and then how many of these, well, we said that there were m a's in this substring y, so y squared will be yeah, well, I guess it's just like a to the m and then another a to the m z. And what's wrong with this string? Well, this string has, well, it has too many a's, man. I just added m a's to a string that had the same number of a's as b's. So now this string just has m plus n a's and n b's. Maybe it's even more clear to say that this string just actually is. This is better. This is better. I think this is true even. Yeah, that this string just is a to the n plus m, b to the n. Yeah, that's true. That's just true. And this string is simply not a member of this language. That is a contradiction, and our conclusion is B is not regular. So step 8 was an analysis of what form x and y must take. And now, if you didn't see it already, hopefully at this moment you realize the value of the pumping lemma. The value of the pumping lemma is that once I ascertain the sort of structure of the repeating part, then I pump it by forcing, so to speak, this machine to accept longer strings which repeat that repeater part. But by pumping it, we create strings which are clearly, by definition, not members of the language. And so we get a contradiction. And in step 10, we conclude, therefore, that this language is not regular. All right. Very, very slow lesson on that topic. Watch at somewhere between 1.5 and 2 speed. Have a nice weekend. Bye.